So, good morning. Welcome to Krishna's classroom. We continue with our exploration of metric spaces. If you recall, last time we gave some statements which are equivalent to the statement that a function from one metric space into another is continuous. Therefore, that in fact suggests other definitions of continuity, because you know that every definition of equivalent to the original definition of continuity, or every statement that is equivalent to the original definition of continuity is a valid definition of continuity. So let us write down the new definition. The new definition is this. Let y dy be metric spaces. Let x belong to x and f be a function from x into y. Then fx belongs to y. We say that f is continuous at x belonging to x if for every open set V containing fx, there exists a corresponding open set U containing x such that f of u is contained in this. In the Venn diagram, this is x, this is y, this is a point x. X gets mapped to fx. Then you are taking an arbitrary open set containing fx. Then what the theorem says is that there exists another open set U containing x such that f of u is contained in fx. Okay. So given V, an open set containing fx in Y, there exists an open set U containing x such that f of u is gets mapped into v. If that is true, then we say that f is continuous. Okay. Now, this is a theorem, or this is a result which we have shown in the context of metric spaces, equivalent to our classical definition that for every sequence xn converging to x, the corresponding sequence fxn converges to fx, as the definition of continuity. But the advantage for this, see, this is a topological definition. The other one uses convergence and the distance notion. Here we could avoid using the notion of distance. Although in the context of a metric space, it is through the distance and through the neighborhoods that we establish whether a set is open or not. And this, of course, something which can be generalized in the context of a topological space. So I think I have already made a lot of statements of this. In fact, I have spent a lot of time how this idea goes into straight away into the topological spaces, and this is accepted as a definition of continuity. I don't want to repeat that. Okay. Now we look at a small application of the definition before we go to introduce the concept of uniform continuity. And I promise you that I will make some statements about some examples in another talk. Okay. So one of the applications is this. Suppose, so you recall, I mean, let me just give the background. Recall that suppose f is a map from R into R which is continuous. Let x belong to R be such that f of x is greater than c. Then there exists a interval that is a neighborhood of where f of x is greater than c. Now this means the following. Suppose you take the graph. Of course, you don't have to be So this could be some domain. Okay. X. Look at the graph of the function. Now, suppose f of x is positive. This is the graph. Now, this is positive. Then, what the theorem says is that you can get some neighborhood of x in which the function will remain positive. Okay. That means if f is continuous and fx greater than 0, then where x is an epsilon positive such that fx is positive so this is x minus epsilon to x plus. Now this result can be generalized. Okay, what is the generalization? We shall generalize this to a real valued function on metric space. So let metric space and x belong to x. Assume let f be a function x from x to r, it's a real valued function defined on x, such that f is continuous and f of x is positive. Then what you can expect, just generalize this. So here it says that there exists an epsilon positive such that x minus epsilon to x plus epsilon, which is a neighborhood, the epsilon neighborhood of x, fx is positive. So then there exists an r positive such that on r f of x is positive. So instead of this, what you are having is this: you have got x, you have got the real line, and then you have a point x where f of x is positive and f of x is positive, and here and it says that there is some interval, some neighborhood of x such that on this entire neighborhood f is positive. How do you prove that? It's simple. Start with the neighborhood of fx. Okay, so let us take an epsilon neighborhood of, or say, okay, what we do is we choose, see, fx positive, so just fx by 2 is positive. Now choose then the epsilon neighborhood of f of x is the interval by 2 okay. So this is b, okay, this is of course an interval, an open interval containing fx in R. Since f is continuous from x to R, there exists an open neighborhood of R positive such that Bxr is a neighborhood of x, and such that and f of that means for every y belonging or x prime belonging to Bx R, f of x prime belongs to 3fx by 2, and it implies x prime is greater than 2, which is greater than 0 for every x prime belonging to P. So this is the generalization of the result. That means this whole R neighborhood of this goes to, has a property that fx in that set is positive. So that's a generalization of the result instead of the map from R to R. But you see how it is obtained as a consequence of this theorem. Now that's the point. So this theorem essentially, that the continuity, the definition of continuity immediately enables us to draw this. So with this introduction, now we want to do some small applications. Look at some important functions which are possible. So I'll just do one of them. Let A be x, where x is a metric space. Of course, A non-empty. A non-empty. Now we define dAx as infimum of and this infimum x is, there is no problem. It's all bounded below by 0. Distance is function is defined 0. Now, before we make further statements about this, what we are going to claim is that on x. Now, before that, we'll just look at a simple example, a special case. Choose x equal to r, and with the usual metric, then you have A to be the interval -1 to it is the open interval -1 to open interval or closed interval, it's a metric. Now let us define this function. How do you define that? So dAx infimum of dx A, where A belongs to the interval -1 to +1. What is this function? Let's try to understand this. First of all, it's a non-negative real valued function. So we are looking at this interval -1 to +1. If x belongs to -1, 1, if x belongs to -1, 1, then dA 0. Why it is 0? Because you have, if you take any point here, you compute all the distances from here to every point is set, then take the infimum. And you see that the infimum exists and the infimum is equal to 0. Therefore, this is equal to 0. Now, if x belongs to -infinity to -1, so it is some point. Then you see that it is the distance from, see, the distance from x to every point of -1 to +1, take the infimum of that, and that infimum will be the distance from x to -1. Okay, so then dA of x equal to distance from here to here. What is that? X plus 1 absolute value. That is x minus -1, and this is the distance from x to -1. Because you see that the infimum is obtained at the point -1. Okay. If x belongs to (1 to infinity), absolute value of x minus 1, where x is some point. So the infimum is obtained here. Okay, so that is the definition of the function. Therefore, what is the graph of the function? Let's draw the graph of the function. Okay, so you see that the function is identically 0 on this, and from then on, see that it is going to be x minus 1. What is x minus 1? This is the graph. Okay. And on this, you see that it is going to be x plus 1. Okay. Sorry, 1. Yeah, it's going to be 1 minus x. So this is going to be what is this? This is equal to, so for any x here, the distance from here to here is going to be x minus 1. So that's going to be, this is negative. Therefore, you see that, so dAx. Okay, so let me define the function. D Ax equal to x minus 1 whenever x is x belonging to minus, sorry, 1 to, this is equal to 0, x belonging to minus 1 to plus 1. And this is equal to, what will be the function? The function is, what is the graph of this function? So you see, you take the point minus 2, minus 2, minus 2, this one is 1. So this is equal to minus 2, 1, and this is minus 1, 0. Okay. One minus minus x. This is equal to minus 1 minus x. Therefore, at x equal to minus 1, this is 0. And at x equal to minus 2, it is going to be minus 1 plus 2. This is the function. Okay. So, for x belonging to minus 1, minus infinity. So, that's the, so the graph of the function is as I have drawn. So, this is going to be dA okay, so let us prove this in general. So what we have asserted is that TA is continuous. See, TA is defined as the set of all distance from x to A where A belongs. Sorry, defined as the infimum of this is defined as the infimum of x to A. Okay, this is the. Now, first of all, you observe, make the following observation. See that dA greater than or equal to 0, and therefore it is bounded below. Zero, which implies you see the following. dxa is greater than or equal to 0 for every A and X belonging to R. Because it's a distance function. Therefore, you see that this is bounded below which further implies that infimum of that is undefined. Because the definition is through the infimum, we have to make some support. Now what we want to say is, so the claim is So let us work out the proof of it. So for x comma y belonging to x and a belonging to a, we have d which implies dAx or day is greater than or equal to d dyx is the same as dxy. Now we are going to estimate this, the function. That is so you take the infimum over a here. So this is true for every a. Therefore, this is true. Okay. And that implies further you have d a y. So then you take the infimum of this, and this is greater than or equal to dyx. So this is less than or equal to dyx. This is our fx. So this is fx minus fy this is what we are trying to prove. Interchanging x and y, we have day dxy. Okay, but dxy is equal to dyx. Because of symmetry of the distance function, which implies That is, dA is a continuous real valued function. Now remark so it's actually this. And x is any point here, and it's the minimal distance from x into any a belonging to a. So you are taking all these distances and then taking the minimum. Okay. Now we can define also the distance between two sets in a metric space. Let when we define what is called the DAB, infimum of a comma b belonging to a belonging a comma b belonging to b of distance of that is essentially the smallest distance between the two sets. So if the sets have an overlap, then you immediately see that the distance is 0. If the sets do not have an overlap, then the distance is non-negative. Okay, maybe positive also. So remark if the sets Okay, or if A intersection B is non-empty, so it does not mean that the intersection is it is if the intersection is empty, the distance may not be positive. All that you can say is it is non-negative. For instance, consider the interval 1 the two intervals 0 1 and 0 2. So A equal to now you see that A intersection B is empty, but still you see that the distance, so in this case DAB is equal to 0. That's quite easy to see. Zero. So this is the situation that I said, that even if A intersection B is zero. So that's something. Now, for instance, you look at this example. So, somewhat non-trivial but geometric example. Let EB if you look at the graph of this function, okay, there are points in R2, cos xy. So you see that if you look at the graph of this, see that xy equal to 0 consists of these two lines. This line. So this is the graph of zero. Now the graph of xy equal to 1 is the hyperbola, rectangular hyperbola. So this is now what is the distance between What is now? This can be easily computed. What you do is look at the points n 0. And belonging to A, and n 1 by n belonging to B. Now, sorry, I think I have drawn the this. Sorry. So the graph of this function is the graph of this function is a pair of lines x equals 0, y equals 0. This is either x equal to 0 or y. This is so here y is equal to 1 by x. Okay, so these are the two graphs. And so what is the distance between them? Now you see that this is A, this is B. Now what is the distance between these two? So you see that d of n0 to n1 by n. This is equal to, what is it? 1 by n. And you see that as n tends to infinity, this goes to 0. Therefore, as n tends to infinity, goes to 0, and which means so that's the distance between these two. Okay. Now I think we can start with the preliminary work for introducing the concept of uniform continuity. Okay, let us start with an example. namely f of x 1 upon x for x belonging to infinity. Note that as x tends to 0, if x tends towards is this a continuous function? Say that the function f is continuous on 0 to infinity if it is continuous at every point. Okay. F from 0 infinity to what is the graph of this one? Let us examine the passes through the 1, 1. This is the graph. So any point on this is x. This is the graph of the function. Okay. Now you see that at each point it is continuous because you take, see what is the definition? Take an x, this is fx, choose a neighborhood of fx, then see do you get a neighborhood of, does there exist a neighborhood of x which gets mapped to? Yes, you get that. So you see that this part essentially goes inside. Okay. So at any x, it is a continuous function. But let us now more carefully examine this. So we have here now we make an observation. The observation is that as x, okay, as x tends to 0. That is, when x goes closer and closer to 0, for a given epsilon, the corresponding delta gets smaller. This is something that we observe. So if you go closer to x, then you see that this is going to be, for any epsilon, this is going to be fx minus epsilon. And the corresponding delta is x minus delta t. This is an observation that we can verify this. Okay. Now, what happens to this? I mean, what is happening here? So, if you examine this, this is going to be, the estimate is going to be this: 1 by x minus 1 by y, which is equal to mod xy. So, if you fix an epsilon such that and take a neighborhood of 1 by x, then you see, as x becomes large, you see that this is going to be this. So this is essentially of the order of zero. Okay. Therefore, whatever be the epsilon you choose, the delta, the corresponding delta will have to be of the order of 1 by x. And that goes to 0 as x tends to 0. Now we will examine this more carefully and these are all our intuitive idea, somewhat supported by the graphic representation of the function. Now let us be more precise on this analysis. Okay, so we'll look at some examples. Consider the function f from 1 to infinity are defined by now you see that one can find out, given an epsilon, one can find out a delta which gives a choice for all x on this interval such that this inequality holds whenever mod x minus y is less than 2. Okay, so we'll examine this. Okay, what happens? Then we have fx minus now you clearly see that this is less than or equal to because okay, therefore you see that continuity is assured, okay, for any given epsilon. What does that mean? That means, you see, in this definition of continuity of real valued functions of a real variable, it is clear that the choice of delta will depend on epsilon. So clearly, the choice of epsilon, that is clear. But does it also depend on now in the above example, or the example that we are looking at, given epsilon positive, there exists a delta a delta positive independent of choice of x infinity, such that where here the choices that does not depend on x. So in this scenario, we say that f is continuous uniformly infinity. So the point is this: we are choosing an x. We are looking at the continuity of this, looking at the definition of continuity of the function f. So once you fix an epsilon, there is a corresponding delta if it is continuous. But can you choose a delta which does not depend on the point x? Now this is the question that you are asking. It's clearly it would depend on epsilon. Okay, and you see that in this particular example, we are in a position to do that. Now let us look at this example 2. Example 2 is again the same function f from 0, 1 to r one by x Now what we observe is the following. Here we assert that one cannot delta such that the continuity we shall prove this. It is enough to show that for some choice of x and y, for a given epsilon there does not exist a choice of delta. Independent of the value of x. For instance, let us see. Choose x equal to 1 by n and y equal to 1 by now fx this is equal to 1 upon 1 by n which is equal to n. given possible. N greater than 1 by 10. Okay. And x equal to 1 by n, y equal to 1 by, then you see that x minus y less than delta this is equal to n. So you cannot choose. See, what does your theorem say? Your theorem says that, see, it is uniformly, or the statement that we want to make, f is uniformly continuous if given epsilon positive, there exists a delta positive such that whenever fx minus fy is less than epsilon, then mod x minus y is less than delta, where delta does not depend on n. Okay. So here you see that as n tends to infinity, for this choice goes to infinity. Okay. So you see that the choice becomes the choice of delta becomes dependent on the point x. Okay. Which is equal to n, and 1 by n minus 1 by 2n This is equal to mod 1 by 2n. Okay. So for a given epsilon, you may not have a choice. Okay. So for a given epsilon, see, there is a choice, delta. What is that delta you have? So you cannot have, so if epsilon is less than n, then you see there does not exist any choice. So for a choice of epsilon which is less than n, there does not exist. In fact, what you are showing is that there are points x and y for which this condition is not valid. Is for epsilon less than n, there are points x which is equal to 1 by n and y for which no choice of delta exists. Okay, let us stop this at this stage, and I will pick it up in my next lecture and then give the formal definition of uniform continuity and then some of its consequences. Thank you very much.